Okay, you've probably seen the other video. I mean, even if you haven't, I guess it doesn't really matter. But this is the practice problem part of these videos. One part theory, one part practice problems, applications. So I've gone 5 questions that are for practice. We've got this one here, this one here. We're going to have to use the graph to actually answer the question. And then these 4 that we just use the information given. Okay, so we're going to start with this question because this is actually a good example of making a datum, which was mentioned in the theory video, and it's also just a pretty easy type of question, classic one that I feel like this is a high school question. I would have done this in high school, so I'd expect most people would have seen this in high school already, but it's still worth doing anyways. So first we need to get all of our information. A ball is thrown up vertically with a velocity of 80 feet per second. So immediately you should be thinking, I need to be using my imperial stuff. So think slugs, feet, whatever other stuff, pounds for forces if we need forces. We don't need forces, by the way. I'm just saying that. At the edge of a 200-foot cliff. So it's already listed here. I know it's kind of blurry, but this is 200 feet right here. Yeah. And then we need to calculate h, the height, from the top of the cliff to the top of the throw. Okay, because the ball is thrown up. So we need the height from the top of the throw. And the total time after release, so after it leaves here, what is the time to reach the bottom of the cliff? So basically the time for this entire loop just like that. Okay. Neglect air resistance and downward acceleration is 32.2 feet per second squared. This, by the way, this is an important number to know. This is gravity in imperial. So you should have this memorized. Like gravity in metric is 9.81 meters per second squared. You should have this one memorized as well. 32.2 feet per second squared. That is gravity. Okay, you should know that by heart. Anyways, so there are going to be 2 parts to this question basically. First part, this is part 1, or part A if you'd like. And then the second part going down 200 plus h meters. This is part 2. Okay. And we need to calculate, for part 1, we need to calculate the time and the height. Okay. And then for part 2, we need to just calculate the time. So part 2 is going to be a lot easier, but of course you need the height to be able to do that. So let's get started. We know that, let me move over here. Can I like pin this? No? Okay, whatever. It's going to go away. But keep this diagram in mind. Yeah. So, oops, that's supposed to stay as a 4. Anyways, let me get to drawing. I'll just quickly redraw the diagram here. We have here, oops, that's too long. We have here the cliff, 200, 200, h, it goes like this. Yeah, that's the throw. And then, okay, so this is it. So we need to first consider a datum. So I'll go back to the image here to speak about that. So as mentioned last time, a datum is your point of reference for all of your information. It'll determine your sign for everything. So the best datum in this case would be here along this line, along the cliff face. So 200 meters up. That's basically saying that this is a distance h up and then a distance 200 down, right? That's how you can read that. So now we go solve the question. Okay, so starting us off, we have v slash equals 80 feet per second, and we have s slash equals 0, because remember our point of reference is right here. So that means when we're going up, this is our 0 meters. I don't know why I'm pointing with my finger. This is our 0 meters right here. This line, this cliff, not down here. While you would think that if you made your datum down here, then yes, it would be, this would be your 0. But we chose our datum explicitly, and I'll put the datum in a different color. This is our datum. This is where we are starting. This is our reference point. If we put it down here, that would just make the calculations really stupid. So we're not going to do that. So we have V naught is equal to 80 feet per second. S naught is equal to 0 meters. And we have that our A is equal to negative 32.2 feet per second squared, right? Because in the problem statement, it mentioned right here, 32.2 feet per second squared downward. As we know, down from the datum is negative. Up, if you wanted to, you could define up as negative, but I just feel like, I don't know why you would do that. So don't do that, okay? So now we look at our formula sheet, right? Let's zoom in on the only part that matters, which is right here, particle rectilinear motion. Oops. Particle rectilinear motion. This is all we're looking at for now in all these problems. So we know we have constant acceleration, negative 32.2 feet per second squared. So we need to look at these formulas and decide which one is going to be best for our use case. So for that, we look at what units we have. We have V naught, we have S naught, we have A. What are we missing? We're missing time. So we have no time. What equation has no time? This equation. And that's how you want to think about these as well. You look at your, you look at what values you have, okay? If you have velocity and you have acceleration and you have time, you would use this equation, for example, right? So you want to look at what you have and then you check to see what exactly it is you're calculating for. So in this case, we're calculating for S. In our case, S is H. Yeah, we're looking for this. We're looking for S up here, also known as H. So we need to calculate S. So instantly you should ignore this equation. There's no S in that equation at all. So don't even think about it. Now look at this. Now you have these two equations. These are competing with each other, right? This calculates S directly. This one indirectly calculates S. Right, now you check what else you have. You have S naught, that's fine. You have V naught, that's fine. You have acceleration, that's fine. You don't have time, right? No time, so you can't use this equation. That's two unknowns, one equation. That you can't do that. You need two equations if you want to have two unknowns. So you move to this one where you have no unknowns actually. I mean one unknown, which is just S. So for this case, we're going to be using V squared is equal to V naught squared plus 2a S minus S naught. Okay? And now let's just plug in our values. So we have, oh, by the way, this is like a theory thing, but when you're traveling straight up at the peak, right, at the very peak, you have no velocity. There is no velocity up here, right? Because if you think about it, in terms of like a graph, it would be like your velocity is starts at 80, right? And gravity is going down, so your velocity is going up, and gravity is pushing you down like this, right? So if we were to like graph this, your velocity would start up here, go like this. Oh, acceleration has caused it to become 0, and then your velocity would then become not 0. It would become negative or something. Yeah, because you're going down, so then it would become negative. Like that, okay? So final velocity is 0. So 0 squared, oops, that's a 3, is equal to, what's V naught? 80 squared plus 2, negative 32.2, S minus 0, right? So this is what we're solving for. And then with some rearrangement, basically you just do plus. So it would be 32.2 times 2, by the way, 64.4. So you'd have 64.4 S equals 80 squared. And then S is equal to 80 squared over 64.4. So putting this into the calculator, you get 80 squared over 64.4. And that gives you S, which is equal to H, is equal to 99.379 feet. Remember, I said 3 significant figures in the theory video. We're going to be sticking to 3 significant figures throughout. So we've done the first part of the question, which was finding H. Now we need to find T. All right. So to do that, finding T. This is, I should put like a line here. Oh, that's useful. Okay. Finding t. So to do that, we look at, again, what is our v naught? 80 feet per second. And we're using the same diagram, same datum, same everything. Nothing changes. We're just going to have to plug in our new values. So when looking at the time it takes after release for the ball to reach the bottom of the cliff, you're looking for the time from A to here. We can call this position B, right? You're looking for the time it takes to make this movement. You're not factoring this part in because that doesn't really matter. Like that's not from the top of the cliff to the bottom of the cliff. That's from the peak of the throw to the bottom of the cliff, right? You're looking for directly A to B, right? So I can add that onto this diagram as well. You're looking for the distance from here to here, just straight line. So how long it takes to go through the 200, basically. It's a bug here, okay. So we have V naught is equal to 80 feet per second. We have S naught equals 0, of course. And then find S final, so S is equal to negative 200 meters. I mean feet, not meters. Did I write meters here? I did. That's supposed to be feet. Oops. And again, A is equal to negative 32.2, right? And we're looking for T. So T equals question mark. And T naught is equal to 0, right? Because at the peak, there is no time that has passed before, like at the peak of the cliff. So again, let's look at our equations, right? So we have V naught. So that's a check here. What are we looking for, though? We're looking for T. So it could be this one. We could use this one. But we don't know final velocity. So we don't use this equation. That's two unknowns. We look at the second equation, right? You're going to have S. We have S naught. We have V naught. We don't have T. We have A. We don't have T. This one works. This equation works. But just in case you double check this equation, we have S naught. We have S. We don't have V squared, but we're not looking for V squared. So ignore this equation. So then we use the middle equation, the displacement equation. So let's go write that down. S equals S naught plus V naught squared T. I mean, not V naught squared, just V plus half A T squared. Okay? And now let's plug in our values. We have negative 200 is equal to, I'm not going to write out a 0, but there is a 0 here. So we have V naught is 80 plus a half, negative 32.2 T squared. And I forgot to write the T here, 80T. Oops. So this is a quadratic equation, actually. So let me just rewrite it as that. So we'll bring over the negative. So half 0.5, 32.2, 16.1. So we have 16.1 T squared minus 80T minus 200 equals 0. This is a quadratic. And then calculators should have like quadratic solvers. So I'm just going to use mine, system solver, or polysolve. Yeah. A is 16.1. B is negative 80. C is negative 200. Right? If you plug that in, you should get two values for T. You'll get T is equal to negative 1.82 or 828, and T is equal to 6.780. Okay, these are both seconds, by the way. So we have two answers, but you're going to ignore the negative one because you can't have negative time. So always ignore negative time, right? That doesn't exist. So your final answer is just going to be T equals this, 6.78. Oh, why did it do that? Okay, I guess it pastes like that. 6.780 seconds. I mean, this should just be 800. Oops. 6.800 seconds. Yeah. I misread my calculator. Anyways, yeah. So always ignore negative times. There's going to be other values where you ignore the negative as well, but that's whatever. Anyways, on to the next question. We're going to be looking at this one, number 4. So let me just do that there. Okay, they can change the numbers, whatever. So we have a function of time we have a acceleration as a function of time, and the function is 2t minus 10. We want to find v of t and s of t, and then we're given initial conditions at t equals 0. We have s naught is equal to negative 4 meters, and v naught is equal to 3 meters per second. Right? So this is actually a really easy question. Let me erase this. Right? We're just going to be using over here, we're going to be using these relations. So this question is really easy. These relations are what we're going to be using. So if we integrate this a, right, that's how we get v. So v is equal to integral, I don't have the symbol, integral a, right? So that means v is equal to int of 2t minus 10. And yeah, we're going to leave this as a indefinite integral. There are going to be times where you will make it a definite integral, but for this question, it's an indefinite integral. So we have v is equal to t squared minus 10t plus c, right? And this is where we bring in our initial condition right here, v naught at t equals 0. So we have v of 0 is equal to 3, which is equal to, if we plug in t equals 0, this becomes 0, this becomes 0. So c. So that means v as a function of t is equal to t squared minus 10t plus 3. Okay? And then now we just integrate again for s. So s of t is equal to integral of v. So that means s of t is the integral, oops, I forgot the equal sign, is the integral of this equation, t squared minus 10t plus 3. So s of t is equal to a third t cubed minus 5t squared plus 3t plus c. And again, we plug in our condition at t equals 0 is equal to negative 4, which is equal to c if we plug in t equals 0. So we have s of t is equal to a third t cubed minus 5t squared plus 3t minus 4. That's supposed to be a 3. There, minus 4. Okay. And that's the question. That's all there is to it. This one's really easy. Okay. Now on to the next question. We have this one. Okay. This is a graph question. And so let's read what we have. Initial acceleration, 3 meters per second squared. That's constant acceleration. And the acceleration then changes with distance s as shown. So this is an a versus s graph. So keep that in mind. Determine the velocity of the motorcycle when s equals 200. So the velocity at this point, right here. So that basically means at this point also determine the value of the derivative dev ds. Okay, so that's easy. This is our initial velocity right here. Okay, this is just some random position. And we want v2. So v1, and we want v2 here. Oh, that was a clean 2. Okay, so we have to calculate this, we use the graph. Split it down the middle. You need to be able to recognize elementary shapes in these graphs, by the way. There's a triangle and a rectangle. There's a triangle and a rectangle. This is area 1, area 2, area 3, and area 4. Right? So now we just need to calculate each of the areas. So we'll move back down here. Another line, I'm just going to call this Q3 because this is the third question we're doing. Anyways, so area 1, and I bring up the picture again, this rectangle, right? So we have a height. As you can see, this goes up by 1 each time. This is a 1, 2, 3, 4, 5, 6. So it's a scale of 1. So we go down here. Area 1 is just going to be 100 times 3. So this is 300 meters, or this is just 300. Area 2, this triangle, right? We're going from 3 to 6. So height of 3, base of 100 is equal to half base times height, right? So a half of base 100 times height. which was 3. So this is equal to 150. A2 is equal, A2, sorry. A3 is equal, we go from 4 to 6, so height for base is 100 to 200, so base is 100. So it's a half 100 times 2, which is just equal to 100. And then area 4 is this area. We have base 100 to 200, so 100. And height of 4, so this is just 100 times 4, which is equal to 400. So those are all the areas. And now we just sum them together. So we're just going to call this A is equal to A1 plus A2 plus A3 plus A4, which is equal to 300 plus 150 plus 100 plus 400, which is equal to 950. Okay, so that is our total area. And now, so we need the area under the AS graph, which we also need to find the derivative at the point, but that's whatever. Oh, so we get this thing, this shape here, and if we were to manipulate it, we would get that the area under the graph, so the area for an AS diagram is half of V, this is V2, so V2 squared minus V1 squared, right? V2 squared minus V1 squared. That's like, yeah. It's like this. The area is like that. But V1 squared is 0. There's no velocity at V1. Because if you think about it here, it starts from rest with an initial acceleration of 3 meters per second squared. What does that mean? If you have a constant acceleration, right, you're going to have, rest. If you have rest, that means zero velocity is what rest means. 0 velocity. So that means V1 squared is just equal to 0. So your area, or A, is going to be equal to a half V squared. It's V2, but I'm just going to get rid of that because it's a lot of writing. So taking this value and this equation, we're going to get that 950 is equal to half V squared. And if we move around the equation, we're going to get the square root of 2 times 950 is equal to V, which is equal to, let's just get the calculator, square root of 2 times 950, 43.589 meters per second is equal to V, okay? And now we're looking for the derivative. And for that, we can look here again. We're going to use this equation because we want to get, what are we solving for again? dVds, yeah. If you look at this, you can actually solve for dVds using this equation. So you have ADS is equal to V dV. We have A over V is equal to dV over ds, right? That's pretty easy. What's our acceleration? Well, we're looking for the acceleration at point 2. And if we check, acceleration is 4. Velocity, we just calculated, 43.589, right? And this is equal to dV ds. So we just plug this into our calculator, and we get that the derivative at that point with respect to velocity is going to be 0.092. 918, sorry, 3 significant figures, is equal to dV ds. So that is that question completely done. And now we'll just move on to the next question, which is going to be this one up here. So this is another question where we are using, we have to do unit conversion. We have the weight of the American flag is 1.55 pounds on the moon. And the acceleration due to gravity is g equals 1.62 meters per second. Okay, so question 1, part A. What is the flag's mass in slugs? So for this one, you will have to, if you're on an exam, they'll usually give you the conversion from mass, like for mass and stuff. But in this case, when I was given this question in class, I mean, not in class, it was for a seminar. I don't recall getting the conversion. So we had to have that in our minds. I know some people had just looked at their notes. Oh, I guess that was allowed. Yeah, never mind. You were allowed to look at your notes. I'm rambling. Ignore what I'm saying. Anyways, so we need to change our gravity. G equals 1.62 meters per second. We need to change this to imperial. So to do that, we just really easily actually, it's a conversion like this, 1.62 over 0.3048, right? And if we look at the units here, this is meters per second. And this one is meters per foot. So this is just a conversion from meters to feet. But this gives us a gravity of 5.31496 feet per second squared. Okay, I don't know what happened to the squared. This is supposed to be squared. I don't know why I didn't notice that. Let's just fix that quickly. Okay. Yeah. And then the weight, you should know weight is also equal to force of gravity, which is equal to mg, mass times gravity, right? So we have our weight, 1.55. We're looking for the mass in slugs, by the way. So 1.55 pounds is equal to m times our g right here, 5.31496. I'm going to like shorten this. Anyways, so we have 1.55 over 5.315 is equal to the mass, which if we just put this into our calculator, divided by 5.31496. Oh, I forgot to actually do the calculation here. So we get a mass of 0.292 slugs. Okay, that's the answer for part A. You're going to need to keep this mass for part B. What is the weight of the flag on Earth in SI units? So this is another conversion. You take the mass, which is equal to 0.292, and you multiply it by another conversion factor, which in this case is 14.59 kilograms per slug. Or it's not slugs, it's slug, but whatever. Like this, and this is slug. As you can see, the slugs cancel, which is equal to, let's just take this, times 0.12 times 12.59, which gives us a mass on Earth of 3. Oh wait, oops, I typed in, this is supposed to be 14, not 12. This is supposed to be 14. Let me fix that in the calculator as well. 14.59, which gives us a mass of 4.255 kilograms. Okay, and then we want the weight. So again, we know weight is equal to mg. So this is m is 4.255. Oh, that's supposed to be a dot. Times gravity on Earth, 9.81 meters per second squared, right? So we just multiply this by 9.81, which gives us 41.8 newtons. There you go. Okay, and that's that question. Really easy question, just some unit conversion stuff, so you don't need to worry about like difficulty in this case. Anyways, now we look at this question, question 2. This one is a fun question. I went too far. Just question 2. This is a fun question. I remember doing this question. Figuring it out was really fun. Okay, I don't know why I did that. There you go. So let's solve A. We have an applied force that varies with x, okay, as given by A. F is equal to alpha x to the power of 5. I don't know why this didn't. There we go. To the power of 5 plus beta t x to the power of n. T is time, alpha and beta are constants. What is the dimension of the constant alpha? And this is dimensional homogeneity stuff and dimensional analysis. right? Because as you can see, express your answer in the form alpha is equal to length to the power of A, mass to the power of B, time to the power of C. Oh, L, M, and T represent length, mass, and time respectively. And then we need to determine what A, B, and C are equal to. Okay, so we start off with, we're looking for the dimensions of alpha, right? So we can do that. And you use these square brackets to like mean dimension. And you can see it's used like here and here. The square brackets mean dimension. So dimensions of F are equal to, now, okay, you would think that maybe you need to include beta, but since we're looking at dimensions, and this is an addition, not a multiplication, the dimensions of this are equal to the dimensions of this, equal to the dimensions of this. So you can just ignore the beta term, which actually really simplifies stuff. So we have this, okay, and x is distance, position, also known as length. So it's L to the 5. We're looking for alpha, so just rearrange. This is supposed to be alpha. Alpha, wow, my typing sucks, is equal to F over x to the 5, like so. Okay, and now we will just change things into their dimensions. So alpha again. Now force is mass times acceleration, right? That's newtons, kilograms, meters per second squared. Kilograms, mass, meters, length, per second squared, time squared. Also known as t to the power of -2. Oh, that's -2. I should really add that hotkey for the power of negative, but I'll do that later. Divided by, okay, and this is x to the 5. X is distance, so length to the 5, like this. So that means alpha is equal to m L to the power of -4, t to the power of -2. And if we look here, we were looking for alpha in the form L to the A, M to the B, T to the C. So we'll rewrite that. Okay, so L to the A, L to the A, so A -4, M to the B, so M to the 1, T to the -2. So here we get that A equals -4, B equals 1, and C equals -2. That's the answer for part A. So this is a really easy question as well. This could come up on exams. I don't remember if it did on our exams, but fun question. Okay, really fun question. Anyways, for part B, okay, we're given that beta is equal to L squared m t to the -3. What is the value of the exponent n in the above equation? So again, we do the same thing. F is now equal to, do I have beta? No, I don't. Okay, I'm just going to use capital B. Beta t x to the power of n. All right. And now we're just going to match up the units. So as we already said, F is mlt to the power of -2. And then beta is L squared mt to the power of -3 times 1t. I'll put xt. L to the n, because x is n, right? So if we cancel some stuff out, m's cancel, one of the l's cancel, okay, and then t to the -3 times t makes t to the -2, so the time cancels. So we're left with L to the power of -1 is equal to L to the power of n, right? So that just means L is equal to -1, and that's the question. That's the question solved. So this isn't really something you're going to be tested on per se. It's more like something you should be able to do on your own. Like if you have a question and you're looking at the formulas, right? We can take any formula. You should be looking at like this constant force, and you should be able to see this is newtons, this is meters. Newton meters is energy. Yeah, because this is work. Newton meters is energy, cosine is unitless, right? But you should be able to read the units of any equation If you can't, that's an issue. You should be able to do that. And the final question, which is this one. Don't ask why I did question 4 as the second question. I just felt like it. So consider the function y of x is equal to x cubed minus 2x squared minus 5x plus 6. Easy. Part A is asking us for y prime. So this is like high school calculus. You should be able to do this. 3x squared minus 4x minus 5. There you go. That's your first derivative. That's part A answered. Part B wants us a second derivative. So again, this is high school. You should be able to do this. 6x minus 4. Just like that. Really easy. So C is asking for when the slope is equal to 0 and the coordinates x, y for when the slope is equal to 0. So again, high school calculus, slope equals 0. Basically, the derivative, the first derivative, is equal to 0. So 0 is equal to 3x squared minus 4x minus 5. Minus 5. And this is a quadratic. You can solve this however you want. If you want to write the quadratic formula out, you can. Personally, I would just use my calculator. So I'm going to do that. Let's go to polysolve. A is equal to 3. B is equal to -4. And C is equal to -5. Solve. We get that x equals -0.786. And also that it's equal to 2.120. Yeah, 2.120. Okay, so that's C. I mean, that's not C, sorry. Now we need to take these numbers and plug them into the original function. So we're going to get, is it going to do that weird thing with the copy paste again? No, it isn't. Okay, good. So we're going to get this cubed minus 2 this squared minus 5 this plus 6 is equal to y of this, which is equal to, and we just put this into the calculator here quickly. I'm going to store this as x, store this as y. Okay, so we're going to have, let me see, x cubed minus 2x squared minus 5x plus 6. This gives us an answer that y is equal to 8.209. Okay? And then we do the same thing with 2.120, but I'm not going to rewrite it. Y of 2.120 is equal to, let me just quickly put this in the calculator. Y cubed minus 2y squared minus 5y plus 6. This gives us negative 4.061. Okay, and as you should recall, if you look at part E, by the way, we need to sketch the curve. So you should be keeping this in mind. This is a maximum because slope equals 0 is either a min or max or an inflection point sometimes. I mean a nothing. The inflection point is second derivative equals 0. This is a min, this is a max because the y value is lower. That's pretty obvious. It's a min. For part D, we want the inflection point coordinates. That's when the second derivative equals 0. So we go 0 is equal to 6x minus 4. You don't need a calculator for this. You can do this. 4 over 6 equals x. 2 over 3 equals x. That's pretty obvious. Okay. And then again, you would just go y of 2 over 3 into the original equation. So I'm just going to do that quickly. 2 over 3 to the power of 3 minus 2, 2 over 3 squared minus 5, 2 over 3 plus 6, plus 6. So that gives you, it's equal to 2.074. Okay, those are your values. And now we're on to E, sketch the curve. Okay, I need to center this better. Here we go. Here we go. We need to go from -3 to 4. So arbitrarily 3 is there. That's supposed to be a negative. -3 is there. Okay, so you're drawing this. You're also going to need to plug in the values like -3 and 4. And 0 to get your x and y intercept. I'm not gonna like show those calculations. That's kind of a waste of time. Also, using the hint, you can see where all the zeros are. So there's a 0 at -2, a 0 at +3, and a 0 at 1. That's what the hint is. So you just go up like this. You hit your maximum here, which we calculated at negative 0.786, 8.209. And you go down, you hit your y-intercept. You go like this. You hit your minimum, which we also calculated. You go back up to your max, and then you go here. This is what your graph should look like. General shape. I didn't actually calculate any values for this. You can intuit that this is going to be negative if you don't want to calculate it. Same thing here. You can like get estimate that this is positive and just know that this is a min, this is a max. Leading up to a max, it's going to be like this. Leading up to a min, it's going to be like this. It's pretty easy to like figure out without actually calculating stuff. So this is what your graph looks like. And that is all. Those are all the questions that I have today. If you didn't understand anything, just ask. I will let you know. Not personally, because I don't know you. But I can explain more in depth if you have questions, is what I'm trying to say. Thank you for watching. Bye.